So today we have a special visitor, Professor Noble from University of Tulsa. And I think it's the best time to present.
Did you know this ahead of time? I mean,
Of course I knew. I know everything in the universe, but I'm just not saying everything I know to everyone. No, seriously, of course, it's a coincidence, but it's a nice coincidence. So you've heard on Thursday about the discovery of a signal, gravitational wave signal from a binary black hole.
Wait, what?
No, I'm not going to say that you're going to talk about it. I'm just saying that. No.
I was preparing my talk.
Wait a second. The point I am trying to make is the following: if you have just gravitational waves, you will not discover anything except that you have those gravitational waves. You need to know counterparts. You have to identify particular systems and then start to observe them with different instruments: X-ray, gamma rays, optical, UV, radio, maybe neutrinos. Unless you actually identify the systems, you're just detecting signal. That's it. You need to know what the systems are to study those systems, and that's what you're going to talk about. Because Professor Noble is going to tell us what is going to happen to the gas around those systems and what kind of signal you may expect these systems to produce. And to introduce him, let me just say, well, he got his undergraduate from Caltech. And Caltech, you know, is a place where all those gravitational business started with LIGO and everything. And then he moved to University of Texas, where he continued to work his work on numerical simulations of binary black holes. And since then, he got postdocs in University of Illinois in Urbana-Champaign, the place for numerical modelers of everything in the universe. And then what else? Johns Hopkins University, right? Second postdoc, and then he worked in the Rochester Institute of Technology, and since last year he is in University of Tulsa. So now the floor is yours, and I guess we're all very much interested in hearing what those black holes are, how they accrete the gas, and what's happening.
Thank you very much. Yes, I'm extraordinarily excited to be here to talk about this subject because there was that particular event that was announced Thursday. It was a little bit annoying though because I had to change a number of my slides. So I usually communicate this as sort of a race. So we're after detecting black hole binaries electromagnetically, and so we wanted to beat LIGO to its game. We wanted to detect them first with light, and now I guess we've lost. We've had some candidates with light for a while, but no really smoking gun per se. So I guess I'm a little happy to have lost that race, but I'll tell you a little bit more about how we can learn more about the system when we measure both gravitational waves and electromagnetic waves. And I also want to highlight some of our, so this is a large effort. We have many experts in numerical relativity. Manuela Campanelli and Josef Slachauer are both numerical relativity experts. And they were one of the first groups they were involved in one of the first groups that solved the two-body problem in GR. So solved Einstein's equations numerically to solve how two black holes merge. And then we have post-Newtonian theorists, Hiroyuki Nakano, and we have other numerical relativists, Bruno Mundim and Miguel Zilao. And then there are magnetohydrodynamic accretion disk theorists such as myself and Julian Krolik, who's in who's an expert on active galactic nuclei, supermassive black holes that are accreting, and Dennis Bowen, who's a graduate student working on this with us at RIT. And the research is described in these papers, and we're supported by various NSF grants, and most of our calculations these are supercomputer calculations that we use the Blue Waters cluster at NCSA and also the Stampede cluster at TAC. So yes, so we usually are looking for light signals, and we were fortunate enough to hear one for the first time. At least, I guess some people were privy to this since September. So September 14th, 2015. That's how you read that event date. And so you really are hearing gravitational waves. You don't see them, right? They're more of an audio frequency band event, and they work more like sound waves. And so they give us a different kind of information about these sources than the electromagnetic information does. So we're really hoping to marry the two modes of information to uncover significant constraints on these particular systems. And the particular systems I'm after are not the ones that were detected. So the ones that were detected in this event were 30 solar mass black holes. So black holes black holes with a mass of 30 suns. We're after black holes the mass of 1 million to 1 billion solar masses. So these are black holes at the centers of galaxies, and we're after how they accrete gas, or how gas falls onto them and heats up and creates light. So I'm going to outline, I'm going to introduce black holes, accretion onto black holes, and our strategy for simulating them. And then I'm going to tell you a little bit about our results, how we've surveyed the parameter space in terms of mass ratio of these black holes, how the initial conditions affect the results. And then I'm going to tell you, show you a little bit about what our recent advances in numerical general relativistic MHD are. And then maybe if we have time, we can have a little discussion on this event. And I've prepared just a couple slides on it. So I hope we get to that. And so what's a black hole? A black hole is a dead star that's collapsed. There's no more fusion to support. There's no more pressure to support the gravitational collapse of the object. And so it just succumbs to gravity and falls and makes a theoretically singularity at its center. It may be spinning, so it can spin up to a maximum spin angular momentum of 1 with respect to its mass. And it's mathematically described through a space-time metric. So this is the Schwarzschild metric, per se. And so it tells you how mass and space and time are distorted with the presence of gravity. And so here's a little animation of the two-body problem. So the two-body problem is a classic problem discussed in classical mechanics. And in general relativity, that was not solved until 2005, 2006, when you need to solve Einstein's equations, which are these sets of 10 nonlinear hyperbolic partial differential equations, and they're very difficult to solve. And it took them 20, 30 years to solve these, to develop the methods and solve them stably so they could actually have black holes inspiral, merge, and then ring down in one simulation. And members of our team worked on this effort. And so the two-body problem is no longer the prime candidate. It's actually the first instance of this happening. So this was the classic example, this event was a classic example of a gravitational wave signal, and that was the first one we've seen. So that was a particular novel aspect of this discovery. And also, if you have gas around a black hole, that gas will light up as it swirls around it and dissipates its angular momentum and its orbital energy. And you'll see some sort of, this is a false color image of the intensity of light that you would see around a black hole. And so people are trying to image black holes around in our local environment, like the black hole at the center of our galaxy. Yes?
When you say solved in two-buddy problem,
Yeah.
do you mean a numerical solution or do you mean an analytic solution?
Numerical solution, yeah. So where I come from, I'm sorry, I hit the mic. Where I come from, a numerical solution is just as good as an analytic solution. If your numerical solution converges at the expected rate, then it's fine. So there are different kinds of black holes. There are small black holes and big black holes. The small ones are sometimes called stellar mass black holes because they come from stars and they're on the order of 1 to 10 solar masses in mass. And then there are supermassive black holes that are, as I said, 1 million to 1 billion, maybe even 10 to the 10 solar masses in extent. The stellar mass black holes, these were the ones observed in GW 150914, and they are often seen in so-called X-ray binaries where you have a star that donates some mass onto the its neighboring black hole, and that gas swirls around and dissipates its orbital energy and lights up the disk, and usually creates X-rays. That's why they're called X-ray binaries, because the gas is so hot. And so we see some of the types of phenomenon in both systems. And for instance, we see jets that are launched from the spin axis, around the spin axis of the black hole, and they're launched by magnetic fields that are wound up in the disk. And both of these accreting systems tell us about the cosmos in different ways. Stellar mass black holes tell us about stellar evolution and populations of stars, and supermassive black holes tell us about how galaxies form and cosmic evolution, that sort of thing. And but both tell us how plasma works in the strong field limit of gravity. So one can inform the other in this sort of investigation. So here we have a supermassive black hole. This is a kiloparsec long jet that emanates from the central engine, which is a supermassive black hole. And you can see the disk that forms around this. Okay. So the idea is that you have this dense disk of material circulating around the black hole, and it emits usually in UV and maybe X-rays, depending upon the size of the black hole. And the corona, just like the corona of our sun, emits in X-rays. And this is the lower density, hotter part of the accretion disk. And then accretion disks often have a jet. So if the black hole is spinning, that spin angular momentum can whip around magnetic field lines on which plasma can then be accelerated down, and you'll get this relativistic jet that emanates. And it's usually very bright in the radio band. And using radio telescopes, we can resolve the fine knotty structure of these jets, and actually peer down into the central cavity of that jet and see phenomenon on the scales of the black hole event horizon. And so in order to do these simulations, you need to put several physics ingredients into the soup. You need ideal MHD. Things are well ionized, so they operate ideally pretty well. You need general relativity because you have black holes. You need some sort of causal surface that represents the event horizon. You need radiative transfer because these are hot. So photon pressures are probably important in some circumstances. And in particular, you want to make accurate predictions of these objects. So you need to do accurate radiative transfer through the material to get an accurate readout of the light that you would expect from these simulations. And then also, sometimes the electrons and the ions do not thermally couple, so they're non-local thermal equilibrium, and so you would need a multi-species thermodynamic model for this. So we've got these two ingredients pretty well solved. We have post-processing radiative transfer available to us. We're working on in situ simulation radiation physics. We just have radiative cooling right now, but we want radiative feedback. And then we're also working on multi-species thermodynamics. So that's where we're at now. We're moving towards adding these components in the future. And so these are the basic physics assumptions, and these are the physics equations that we solve. So many of these equations you're familiar with if you're familiar with the Euler-Lagrange equations of hydrodynamics. So you have mass conservation. So the continuity equation is just this top line. And then you have an energy equation, which is the time component of your stress energy, the local conservation of stress energy tensor, local conservation of energy. And then you have the spatial component of that is the momentum equation. And then Maxwell's equations, when you couple them with the fluid and assume that it's a perfectly conducting plasma, just reduced to pretty much the induction equation. So an evolution equation for the magnetic field. There's a constraint, though. There are no magnetic monopoles, as we all know, and so the divergence of the magnetic field has to be 0. So this amounts to a constrained system of nonlinear partial differential equations, and we monitor that constraint by careful orchestration of how we finite difference our equations of motion. All right. So one thing I want to point out is that we let energy leak out of the system. So we use so-called high-resolution shot capturing methods to solve these equations. I won't bore you with all the technical details, but they're very good at conserving mass and energy. And it's important for understanding how shocks travel through gas that you conserve things well so that you don't artificially heat the material and artificially alter the thermodynamics of the system. So our code is good at conserving these quantities, but we want to actually model the effects of radiation energy loss in the system, right? Because the system is going to be hot, it's going to be radiating, that light carries off energy, and we want to cool the gas through this mechanism and see how that cooling affects the dynamics. And so that's what we do. And we calculate that energy, so we capture it, we record it on disk, and then we use that to inform our radiative transfer equations and in order to calculate how much light we get from it. Okay, so it's a self-consistent model. So any radiation losses actually goes into our radiation prediction. So an example of what an accretion disk will look like, this is a disk around one black hole. So the event horizon is this white line. Our simulation actually penetrates the event horizon. So we use so-called event horizon penetrating coordinates, or Kerr shield coordinates. And we cool the disk. So if the disk weren't cooled, the disk would puff up and get thicker and thicker. So this is a cross-sectional edge-on view of the disk. This is the log of the density on this color scale. The units aren't important. And the time is in units of m. So all the time and length scales of this problem all are tied to the mass of the black hole. Okay, so the curvature of the black hole, curvature of the space-time that the black hole creates is all scales with the mass of the black hole. So pretty much all the physics is scale-free, is independent of the mass of the black hole. The only physical length scale that is that then, in order to set the units, you need to. So if you wanted to introduce units, or if you wanted to look at specific properties of the radiation, you have to then set the mass of the black hole. But if you wanted to just study the MHD on a curved space-time, you don't care about what the mass of the black hole is. It scales out of the system. So
What's the energy scale in the problem?
the energy scale of the problem.
Yeah, you've got a density in front of us, but everything's relativistic. How relativistic?
So there are two ways of measuring how relativistic something is. So the compactness, so how much mass you have in a certain radius. So the matter is not relativistic on that sense, but it is moving at a like half the speed of light when it's near the horizon. Is that the sort of figure you're after, or?
You have local equilibrium much of the time. How do you have MHD without some assumption about fluids and equilibrium? So.
Yeah, that's a good question. So our cooling scheme assumes that, so the scale height, so this is the height over the radius, so this is the angle opening of these lines. So we're after a specific thickness of the disk. So the thickness of the disk determines whether or not you're in a gas pressure dominated regime. And so if you're in a gas pressure dominated regime, then your disk profile, the height of the disk scales as the radius, the radial location of that height. So H over R is about constant. But if it's radiation dominated, so if you're around a smaller black hole, for instance, these aspects scale weakly with the mass of the black hole. But a lot of the physics, so there are there are radiation effects that do scale with the black hole, but a lot of the dynamics don't. So for a radiation pressure dominated disk, you would have a constant height disk. Okay, so it depends on what regime you're in, and it depends on the accretion rate, how much gas you're accreting from the outside. That determines this too. So I'm smearing out a lot of background information to give you kind of a conceptual idea of what we're doing. So please do ask me a question if there's if you have any questions. I'm missing a lot of information here due to time limitations. So I just want to say that our simulations connect to observations pretty well. So we see these optically thick disks that create this multi-temperature black body spectrum. So this is power at a specific frequency versus the energy of the radiation. And so this is our simulated spectra using Monte Carlo radiative transfer through a corona. And by varying that density level, so that density level is a tunable parameter of our system right now because we don't have radiation feedback in our simulation. When we tune it, we recover what is observed qualitatively. Okay, so it seems as though the physics that we're connecting to what more or less what's going on here. Okay, and this is just a model of the Bremsstrahlung radiation that comes from our simulations. So the red emission here are soft X-rays, and the blue are the hard, more energetic X-rays. Okay. So binaries. Okay, so we can hear gravitational waves. All right, I can say that. It's no longer I would say it's no longer in question, but I guess we need to see more of these events to be convinced entirely. We can see black hole binaries in different frequencies, okay? So as you increase the mass of the black holes, you decrease the frequency of their waves, okay? Because the radius of their separation scales with the mass. So they become, the period, I mean, you can just use the Kepler's law, the period scales with the separation. And so the supermassive ones that we're trying to simulate are not in the LIGO band, they're in a band at a much lower frequency. So we're hoping that there will be this space-based version of LIGO called LISA, or ELISA. It's also called NGO, New Gravitational Wave Observatory. Right now, ESA, the European Space Agency, is developing the idea. NASA was part of it originally, but backed out. So the hope is that effort from NASA will be reinvigorated. And also, at even lower frequencies, for even the most massive binary black holes, we're hoping to hear gravitational waves with pulsar timing arrays. So these are pulsars, neutron stars, beaming radiation at us. So we see this periodic lighthouse effect sweep past us. So they're very accurate clocks. And if a gravitational wave transits in between us and it'll fluctuate that time. And we can measure that fluctuation, and then we can correlate the fluctuation we see on other pulsars and triangulate the passage of that gravitational wave between those multiple pulsars. And we can coordinate all this and create a pulsar timing array, and then we can measure gravitational waves this way. So there are these instruments that will hopefully fill in this whole long, wide bandwidth of gravitational wave information for us. And so LIGO is going to be observing more, and it's going to become more sensitive, so we expect to hear more from it. And actually, the event rates have been improved a lot. So before, it was a larger window, and now it's constrained a little bit more, and it's constrained to the higher end. So we were expecting to actually see more events than we had been before. After all, the event happened just, a couple weeks after it turned on. So, all right. So, as I said, we're hoping to see electromagnetic information from these gravitational wave events. It helps us constrain the models better. So, one uncertainty when we view a system is that we don't know what the masses of the black holes are. But the gravitational waves tell us that information very well. They also tell us the spins of those black holes and their orientations possibly. So all that information can then be assumed in our simulations, and then we can make accurate predictions of the light from them. However, we still have assumptions of what distribution of gas, level of magnetization in the gas, and in a variety of things. We're hoping that all those choices lead to pretty much the same outcome in our simulations, but that's for us to see. And I'll be talking a little bit about how we're finding that to happen. So all this information will help us constrain each of our models. So even our light observations of light can help us localize the gravitational wave signal. So if we're seeing a variable electromagnetic source in the ballpark region of LIGO or LISA's detection, LISA and LIGO do not accurately constrain the location of the event on the sky. So if we saw a variable source that seemed more or less like it could be a binary, then it could help inform the properties, the information of the binary via the gravitational wave information. So more information is just better usually. Right? So that's what we're doing. But we can also, so the gravitational waves tell us the luminosity distance. If we see electromagnetic signal from its vicinity, then we can record a redshift. Okay, and then we can have a different means of connecting redshift with distance. And so we can then actually then we can verify that the redshift distance relationship that supernovae have informed us, whether or not that is a good measurement. Okay, so it's a totally different means by which we establish this relationship. Yes, and so no longer will seeing an electromagnetic event from supermassive black holes be the first of its kind for black hole binaries, but it'll be just the first of its kind for supermassive black holes. So I have to qualify all of our results now. So we have seen two black holes near each other, spatially extended from each other in space. And there are several instances of these, but all of these instances are relatively far apart still. So they're as anything is, they're emitting gravitational waves, but they're not strong enough sources yet to be detectable even if we go into space. So we want to see objects that are even closer together, right? We would ideally like to see two black holes in spiral for a couple of years and then merge and then ring down. We want the whole thing, okay? And we want to then be able to predict, right? We need time to get ready for the merger. And so we need to also make sure that our models are consistent with the inspiral part of the orbit. And then we want to then train all of our telescopes so that we capture the merger event. And so we need these things to be relatively close so that they will inspiral within Hubble time or within the age of the universe. And these objects are way too far apart, okay? And in order for them to get closer, we won't be able to spatially resolve them anymore, okay? Because these are distant objects, right? We don't have supermassive black holes floating around, our solar system, or, thankfully.
What's
But
the difference in your modeling?
We have two binary black holes. Haven't they already swept all the gas out? Why are we seeing X-rays?
okay, so these would be considered dual AGN. So an AGN is an active galactic nucleus. It's just a supermassive black hole that has gas falling onto it. That's bright. So if you have two of these let's say you have two galaxies merge, and each one will be an active an AGN for a while, until they get close enough that the gravitational torques fling out material. Right, and you'll see that in our simulations. So yes, that's a good point. So eventually the black holes will get so close that it'll just expel material from its vicinity. Our simulations, though, have suggested that actually, and others have suggested that the magnetic stresses are amplified in this situation, and they allow the material to follow the inspiral. So you'll have a significant amount of material up until merger. So.
What's the issue in your modeling, or what technical issue comes up that causes you to be talking about supermassive black holes that are harder to work with, more rare? What does it make any difference to you as a numerical modeler? Which system you look at?
Oh, yeah. I'm sorry. I didn't mention this. So we don't. So many of the formation models of stellar mass-sized black hole binaries suggest that they will rapidly accrete any material that's in their vicinity. So there will likely be no electromagnetic source around them near the time of merger. So that's why I don't focus on stellar mass. But
does it make any difference to your computer simulation?
not really, not at this point. It doesn't. No. But once we enter radiation feedback, then it would matter. We just have to adjust the parameters, but we could adjust those parameters. Yeah. So it doesn't. So for instance, if there were detections, electromagnetic detections from this event, we could start comparing to those. So far, no one's seen strong evidence for that, at least for this particular event. But I hope people do look for that in the future. So we can't look to spatially resolve these things, so we have to look at other means. So we can do this photometrically, so we can look at the light curve that we get from these objects. And this is what we see from one particular object was found using the Catalina real-time transient survey. So the object is, the point of these transient surveys is that some are transient events in the universe. They're short-lived, and we want to capture them because they're usually very interesting. And so these robotic telescopes scan the sky and record this data every night or every other night, and then you look for time derivatives of the light. And so one time derivative fell out, and it followed this nice periodic curve, which is actually seen at different wavelengths. Okay, so. And in particular, this one, so these are all the parameters, so it's at a redshift of 0.3. The rest frame period is 5 years, okay, so you have to redshift that if you want the apparent period. The masses are about 10 to the 8, 10 to the 9, so they're pretty massive. And the separation is around 140 m, so m is the total mass of the system, right? So dynamical aspects of the system scale with the mass of the black hole. So they're so far apart that they won't actually inspiral for another million years. So it's exciting, but not exactly what we want, right? We want the merger to be seen. So, but this is a pretty good candidate because it varies on the right timescales as a binary black hole would. And the interesting thing here is that they see a time lag between the infrared and the visible light period. So that time lag is explained as a reverberation of the visible light signal coming from the interior. It reverberates or echoes off the further out material, and it is reprocessed, turned into infrared light, and that's what we see. So this is consistent with models of AGN disks, that there would be some dust that would reprocess it at this distance that is determined by the travel time of light to this radius, which is the time lag. So that's particularly interesting. And there's another event which has a much closer separation, 14 m. So actually at 10 m, two black holes will merge in about 10 orbits. And so this thing is going to merge fairly soon, and in our frame, it'll merge within 20 years, and so this object is really interesting, and we'll be following it too. And more observations of it will be taken. We'll take the entire electromagnetic spectrum of it and look for jets. So maybe jets are coming out from each black hole, and we can look for those too, and connect with our simulations. Okay. And LSST is another transient sky telescope. It's a large synoptic all-sky telescope or something like that. I forget the acronym, but it's going to be it's going to be taking a whole sky's worth of data every 3 days. Okay, so it's going to kind of revolutionize this kinds of science. So it's expected to see thousands of these kinds of AGN. So this is potentially going to blow up in the next few years. So these are relatively rare events, and we have many models to explain them, so we need to make our models more sophisticated, and we need more data. Okay, so that's the name of the game that we're trying to play. So we need to do supercomputer simulations of these things so that we know what to expect. And we need MHD because that is what explains the magnetorotational instability, which explains the high accretion rates that we see in nature. And in order to do MHD turbulence, we need 3 dimensions because in two dimensions, the turbulence decays quickly. And we need to do all spans of gravity, actually. We need Newtonian simulations, post-Newtonian simulations, and also numerical relativity simulations. And we're choosing to do post-Newtonian simulations because we want to, that allows us to look at the black holes, but it also allows us to see how the black holes inspiral, okay? So we plan to transition then to a numerical relativity simulation once the black holes are close enough, okay? So that's our strategy. And we found evidence with our MHD simulations. A lot of this theory that had been developed before us was all in either 2D viscous hydrodynamics or analytic 1D theory, so-called alpha disk theory. And it predicted that, yes, at a certain radius, the black holes would start, they would enter the gravitational wave dominated regime where the inspiral rate was dominated by the release of gravitational waves, the energy loss of gravitational waves, and it would just run away from the accretion of the disk. And so you would be left with this gap or this vacuum between the merger event and the disk. However, we found that magnetic stresses get enhanced in this process and allow the accretion to follow the inspiral down to very small separations, much smaller than what the alpha disk theory predicted. So MHD is really important for that. And we have some sort of radiation model that allows us to connect our simulations in a more robust fashion to predictions. Okay, so I've explained this a little bit. So we have two black holes at the center of two galaxies, and those galaxies merge, and they're embedded in all this gas and stars, and that interaction allows them to fall towards each other faster and form a tight binary. That binary will then be surrounded by gas from stars or just from the galaxy itself, and the time-varying quadrupole moment creates this gravitational torque on the gas that flings gas out, and you can see this arm-like structure occur. This is a movie of ours, so you'll actually see the black holes in spiral, so the frequency increases. And so matter is drawn toward each black hole, and some of that matter is flung back out into the disk, and that matter then collides and shocks and heats up the disk, and that can lead to an electromagnetic signal. So there are a number of groups doing this. We're in this regime that unifies Newtonian evolution with general relativity, and is really important to match the two. And we have members that have experience in numerical relativity and codes, and we've developed some of these codes, and we're hoping to then eventually just interpolate our data onto a numerical relativity calculation and run with that, so that we can actually continue off and do the full numerical relativity calculation. The reason why we don't just do a numerical relativity calculation is that they're time-consuming and expensive, and don't accurately track conservation of angular momentum very well, because they usually use Cartesian grids. So you can ask me more about that later if you want. So we do this calculation for many orbits in the post-Newtonian regime, and we do it very accurately, conserving angular momentum, so our energy, our light curves are very accurate. And so in order to provide a gravitational model, we solve Einstein's equations, but we solve them perturbatively, and which results in a post-Newtonian expansion for our space-time metric. Okay, and so how do we evaluate the performance of this metric? Well, we calculate this Ricci scalar. Yes?
So what's the definition of post-Newtonian?
Post-Newtonian is, okay, so as the black holes get closer together, so when they're far apart, everyone would say that they're in the Newtonian regime because they're traveling at a very small velocity, okay, and their radius is not going to be decreasing fast, okay. As you get to higher velocities, so as v goes to c, the speed of light, then you enter the relativistic regime. Okay, so once the black holes start orbiting at a velocity, orbital velocity of a fraction of the speed of light, then you have to do either a post-Newtonian calculation or a numerical relativity calculation. So you expand, the perturbation parameter that you expand about, you expand with, the perturbation variable is is V over C squared. So the order of accuracy of your post-Newtonian calculation, the first order calculation is accurate to V over C squared. 2pn is V over C to the fourth, and that's how it's counted. So we're at separations that are close, but not too close. Okay, so these will be orbiting still for tens to hundreds of orbits before they inspiral. And so this Ritchie scalar, so since they're black holes, the Ritchie scalar is supposed to be zero identically if it's a solution of Einstein's equations. The Ritchie scalar kind of tells you how much material is present in the space-time. It's like a mass density, so to speak. And so it should be zero, right, because there's no mass. They're just two black holes. There's no mass outside of the event horizons, right? There's mass at the singularities, but not around them, because they're called vacuum solutions because they're just point masses. So the Ritchie scalar is supposed to be zero, but it's not exactly because this is a post-Newtonian expansion, but it decays fairly rapidly to small numbers. So we're pretty confident in this evaluation that this is done pretty well. Okay, and this closed form, so all we have to do is feed it a time and a position, and we get back the metric. You can't do this with numerical relativity, right? You have to evolve from one time to some future time, all these partial differential equations, but with this PN prescription, you can actually do that. And that allows us to tailor our numerical grids to the material flow. Okay, so we can focus on just the matter when we do this. So this is the type of thing that we get. This is the log of the density in the midplane. Okay, this is a top-down view. The black holes are circulating. These are the 2 points, are the black holes. We excise, we remove any stuff that happens within this sphere that surrounds the black holes, and that saves us computational time. We're now putting them back on the numerical grid so that we can see how matter falls onto the black holes themselves. But this gives us an idea of how the matter evolves in the outer parts of the disk, okay? And each simulation costs about 1 million SUs. So, because we want to do these for multiple orbits. So we found this really high Q electromagnetic signal from one of our first runs, and it is connected to this overdensity region. So this is the surface density. This is height integrated density from the midplane. And so it tells you how much material is at a location and radius and azimuth. And you see this lump develop, this overdensity region develop. And you see that some of the material from that lump is accreted, but then it's flung back out into the lump. And this movie is in the frame co-rotating with the lump. Okay, so the lump's not supposed to move. Actually, it's orbiting the binary like this, but it's orbiting at a slower rate because of Kepler's law. Right? The black holes are moving past it faster than it's orbiting it. So there's this peak is a beat between the orbit of the binary and the orbit of the lump. Okay, so each black hole is traveling past that lump at the same way because it's an equal mass binary, and so it's pulling off that material and flinging it back out just as the other one would. So it's twice the beat frequency of the two rates, the two orbital frequencies of the binary and of the lump. And so it's neat that it's not at just the orbital frequency of the lump and not just at the orbital frequency of the binary. So it's something that you could only predict if you actually did the simulation. Okay, so this is the type of thing that we're after. This is
One lump.
Why one lump?
One lump. Is that just generic, or do you have lots of lumps?
That's a good question. So power spectra of turbulence is usually some power law. So you always have most power at the largest scales. So my hypothesis is that the largest scale here is just overwhelming the lower scales. So the m equals 1 mode of the azimuth is dominating the future, and it grows. We'll see that this lump is not generic, though. So we looked at different orders of accuracy of our gravity model, and we found that more or less the lump remains the signal we find. So this is the Fourier transform of the light curve of the signal. Okay, I forgot to say that. So this peak shows you how significant a period is in the light curve. And we found more or less that if you decrease the accuracy of the gravity model, you get more or less the same lump. So it seems as though the MHD is dictating what's going on here, at least at these separations. So our truncation of the post-Newtonian expansion was sufficient. And so this is just a line curve of the surface density. And here are top-down views of the surface density. You see it's a little bit weaker in the in the lower orders, and that could be because the tidal torque from the binary is a little bit weaker because it's a lower order model. And I'll skip this for now. This is the plasma beta parameter. We've also done a mass ratio survey. So you can change the masses, the relative masses of the black holes. And here's a movie from t equals 0. So you have to let it equilibrate after a while because you start from a reservoir of gas, but you then have to let the gas get turbulent. And once it gets saturated, then you can start modeling that as something that occurs naturally, right? Because in space, these things are happening over millions of years, right? So they've had lots of time to equilibrate. So we found that this lump doesn't develop as strongly in the smaller mass ratio runs, and it's probably because the secondary becomes a weaker perturber of the flow. Okay, so this peak diminishes with mass ratio, and then it just vanishes pretty much at Q equals 0.1. So when one has 1/10 of the mass of the other. And you don't see any visible appearance in the surface density. So it pretty much goes away between mass ratio of 0.5 and 0.2. And this is consistent with others that have done Newtonian runs and numerical relativity runs. So we seem to be getting kind of a consistent picture. There are subtleties that are different. And one thing that may be happening, though, is that the lump that's formed is not receiving enough magnetic field that can tear it apart. Okay, so magnetic fields create this internal stress that allows fluid elements to lose angular momentum and accrete onto the black holes. So if you lose magnetic field, then you won't have that internal stress, and you'll get buildup of material. So one idea is that we don't have enough grid cells to resolve the MHD dynamics, and that diminishes the strength of the magnetic field. And this is inevitable in some situations, and so we wanted to see if we could introduce an ample supply of magnetic field. So by increasing the disk size, the reservoir of gas and magnetic field, if that has any effect on the lump. And so to give you a perspective, this is the original run, and so we just blew up the disk, so it's much bigger. So this was already a pretty big disk, but now we made it gargantuan size. So I can show you the full movie later if you want, but I wanted to point out that the unique signature there. So we did 2 runs, so one with a bigger disk and one where we just took the simulation and we added magnetic field, ordered magnetic field on top of it. That's rather artificial and arbitrary, but it allows us to see if the magnetic field has a direct role. In both of these cases, the bigger disk and the flux injected case quashed the signal. Okay, so it seems as though there could be instances where a disk is accreting a lot of magnetized material, and then the material becomes more and less and less magnetized, and so then material starts piling up and then could form this lump that then could create this powerful signal. So it could be a natural phase seen in some circumbinary disk simulations. So we're kind of excited by the variety of dynamics we're seeing in these systems. And here you see that the lump, in fact, the signal isn't there, so is the lump present? And in fact, the lump is not present. So we don't see large power at those long wavelength modes. And why do I think magnetization has a role? It's because we looked at the plasma beta parameter. This is the ratio of the gas pressure to the magnetic pressure, or the energy density of the magnetic field. And so if the magnetic field was dynamically significant, then beta would be small. Okay, and here beta becomes really high in the lump. Okay, and when you don't have the lump, it's a nominal level. Okay, so this is providing kind of a consistent picture. More experiments, I think, need to be made to really say for sure. We're trying to put the black holes on the grid. I'm sorry, I'm running a little bit late. And we're doing this using two different techniques. One is this warped coordinate system, so where we kind of pinch the grid lines together around each black hole so that we can resolve the turbulence scale around each black hole. And this is just, I'm playing with the parameters of the grid, showing you that we can control all aspects of this pinching. And so the idea is that we pinch it around both black holes here. And we've done simulations. Okay, so here I'm measuring how much magnetic field is diffused. If you have a loop of magnetic field and you evect it through some space, that loop shouldn't diffuse away, right? It should be advected perfectly, but numerically there is some diffusion. And the diffusion decreases with increasing resolution. And our warped scheme, you can see the grid lines here a little bit, they're focused around that field loop. And so this is a zoomed in view of this plot. And so you can see that the level of the magnetic field doesn't diminish as much as the uniform grid one. Did someone have a question? Yes. Yeah, sometimes they do it diagonally. I didn't have a nice movie of that test, but we have done that test. We've done a test where we've kept the warp part static and we've advected the loop through it, and just to make sure that our numerical methods are working, and it does advect through it okay, but it still significantly diffuses. So, right, it's going through different resolution levels when it does that. And so we've put all this together. Now we can resolve the flow of plasma onto each individual black hole. The scales are really disparate, right? These are large dynamical range simulations. And we want to evolve these for many, many orbits. And so this is just a test right now. We're trying to improve upon our method to do a full run before we use our SUs. So these are really expensive simulations. So we want to be careful with how we use them. We use our allocation. So that was the density. This is just to show that this is actually magnetized. This is the magnetic pressure. So. If we weren't resolving the black holes, you would see this huge entropy explosion around them, because the evolution would be unstable, and you don't see that here. So we're resolving the dynamics. That's a weak indicator that we're doing things right. And another way of doing this is to, instead of having one continuous coordinate system, let's do multiple patches of coordinate systems. All right, we put a cube or a rectangle around a black hole, but then we want to make the disk. We want to evolve the disk in a spherical-like grid so that it conserves angular momentum very well. So that's the idea that we're having, and these are spherical explosions that were evolving through this heterogeneous grid structure. And here, this is a slab symmetric shock that travels through on a spherical domain, background domain, through a Cartesian domain in the center that eliminates the coordinate singularity at the origin of the spherical coordinates. Okay, if you were to do this in just spherical coordinates, this shock would wrap around the pole that exists at the origin. Okay, but since we have a Cartesian grid there, that eliminates that coordinate singularity and allows us to evolve the shock through that point. Okay, and this is technology that we need to do the whole problem, circumbinary disk problem, but also other problems like tidal disruptions of stars. So we'll have a star interact with a black hole and get disrupted, and that makes a circumbinary, a stellar debris disk around the black hole. And so in conclusion, we've seen an interesting electromagnetic signal that we hope to identify in nature. It does seem to depend somewhat on initial conditions and mass ratio. So it's, I think, an important clue as to some of the diverse phenomenon that can result from this kind of system. And we're working now on to advancing these calculations further. And we're also looking for students. So if you're interested and you're an undergraduate student that wants to join a small PhD program that's growing, please talk to me. So thank you very much.
So any questions? Michael?
Does the black hole get charged?
Yes, you can have a charged black hole. So because the electromagnetic force is so strong, it tends to attract its opposite charge, and so it tends to neutralize over time. So at any one moment, though, it will likely be minutely charged. But that effect on the curvature, the gravitational curvature, is minute, though. Yes.
What's the observational signature of an object that you are simulating here? You got all kinds of detail.
Yeah.
I can't imagine there's going to be much detail in the first observation. But maybe I'm wrong.
The
How
first
do you know
observations
how do you know you've got black hole binary system?
Right.
What's the data have to look like to be convincing?
So I think you need to have a variety of information. So right now we're modeling the light curve only. So that's just a scalar number over time. Right? We would like to know the polarization of the light that we get from this object. So if you do a radiative transfer calculation, you can see that there's some non-trivial amount of polarized light from these systems. You also want the intensity of light at all electromagnetic waves, all wavelengths that we measure. As a civilization, we want gamma rays. We want predictions for gamma rays, X-rays, radio waves, and we can do that with our simulation information because we have the state of the gas. So we can predict what the electromagnetic emission is over all these wavelengths. We also want more spatial information. So we hope to better spatially resolve these. Does that answer your question, or you're looking for a more specific answer? We're working on getting the spectrum.
You're modeling the system.
Yeah.
So you want to have features of the data that show that your model is describing whatever the pulses or the radiative information is.
Well, if there are astronomers measuring recording spectra of these objects, time series spectra in the time series and also polarization. And
Okay, so we got all the simulations, and
are
you're
you
just looking for data that confirms that this thing is different from, or is a binary system.
Yeah, and how to characterize that binary from this information. So,
Well, in the gravitational case, you got signal of gravitational waves.
okay,
Then there's detail in that signal that they use to see if it's consistent with simulations of the gravitational emission
Right.
from a binary system. And so
That's more or less what we're doing with
they've shown that there is agreement between models with given parameters and the signal they see.
right, and that's what we're doing with
And
light.
you'll do the same kind of thing with, except you don't have the assurance that they at least have a gravitational wave signal, which is unique and never been seen before. And you're looking for something that's seen all the time, which is optical, or at least electromagnetic, but it's going to have a much different signature from anything else that could, it'll stand out. I mean, this is going to hit you over the head when you see the...
Sure, yeah, that's an important point, right? It has to be different enough so that it is not degenerate with another system, right?
Yeah.
So there, right, as I alluded to a little bit that, yeah, there are right now multiple explanations for that periodic light curve that has been recorded. So we need additional information to see if those interpretations separate. So some models won't predict
Yeah.
features that will be observed in the future from that object, or at least that's a hope. If we saw gravitational waves from these systems, or if we didn't, and we should have, then it suggests that there isn't a compact binary there, right? That it could be just some sort of periodicity in the disk. But if we do see a gravitational wave signal from these supermassive binaries that were the light curves that I showed you, if we saw gravitational waves, then we would know more or less the masses, their spins and orientations, their separations, and that would then be an input to our model, and then we could better constrain our matter initial conditions.
Other questions?
Well, we're also searching for smoking guns of these binaries. So, so far the simulations of the mergers don't have really a momentous, they do peak at merger, the electromagnetic light, but it's not overwhelming. So, and it could be smeared out through optical depth effects, so opacity. So, yeah.
I actually have a question. Do you expect any neutrino signals from the mergers? Is the density big enough?
I think there should be something there. I've not explored the nuclear physics side of this, but we should.
Well, more questions? If not, let's thank our speaker again. And quick announcement, if someone wants to join us for the dinner, just let me know. Scott's gonna leave pretty soon, so it's gonna be a early dinner.
Thanks for all your questions. If anyone wants to talk about the event, I'd be happy to.